Yes. So if you're not speaking, kindly mute yourself because there's some background noise. Okay, so we have officially started, so I'm going to record. Okay, so I'm going to, okay, good morning, good afternoon, good night for everyone who is online. I know everyone is in different areas. So this is the first Zoom meeting, and we are going to have the next one after 2 weeks, because the first units are 2 week long. So we are going to keep as more discussion, open discussion about the topics we are going to cover, because the lectures are pre-recorded, so you can watch the lectures and make a notes and make your questions. So let's start. So, and also I'm going to record this one, so all of these meetings are recorded and they will be uploaded on the e-learning. And there's so you'll have a separate unit which says the recorded videos, and then you can watch them later. So anyone has any questions for what we have covered so far? Any questions? So if you don't have questions, so I'm just going to go through the lectures, the slides we have covered so far. So the basic concept of neuromounting, all the signals which are produced in the body, they are very, very small. They are in microvolts. So, and then we want to record those signals and display on the screen, and also analyze those signals. These signals are very, very small. And when we are working in the operating room or the ICU, we have so many different sources of noise. So in US, all the sources of noise are at 60 hertz. But in Europe or Asia, so if you're in it, they're running at 50 hertz. So all the electricity is at 50 hertz. So you have 50 hertz noise in Asia and Europe. But in US and some other countries, they're at the 50 hertz, 60 hertz noise. So we have in the operating room, we have operating table, which is electrical. We have lights, we have microscope, we have C-arm, X-ray machines, we have anesthesia machine, we have IM machines, bear hugger, blood warmer. There are so many different things. Everything is causing 60 hertz noise. And we are trying to get a very small signal which is produced in the body between those signals. So what we have to do is we have to get rid of all the noise. So we need to use an appropriate filters. And so we should know about what are the filters. And then we have to use the differential amplifier and then amplify them. So the function of differential amplifier is to differentiate between the two inputs, and it amplifies only the difference. So only the difference between the inputs are amplified, but the real signal is not amplified. So the main topics we should cover, or we should at least understand, is the listed here: the current, voltage, resistance, impedance, conductance, Ohm's law, frequency, what are the filters, and what are the effect of filters, because all these will affect something we cannot change, but there are many things that we can change, and that will affect our data acquisition. And we want to have a better signal acquisition, and we do a better recording. And then sampling rate, Nyquist frequency, constant current stimulation versus constant voltage stimulation, and what is the differential amplifier, and what is the function of the differential amplifier. So conductor, the simple explanation for conductor is any substance, any material that gives up electron easily. So the movement of the electron is free movement, and these are known as conductors. So anything which has a good movement of the electron, such as metal, gold, copper, water, blood, CSF, all the liquids. So they have a good free movement of the electrons, so they're good conductors. And then we have a bad conductor. So the one which does not give up electron easily, they are bad conductor. And then we have a insulator. So there's no movement of the electrons at all. So rubber, glass, wood, skin, and even the skin is considered as a bad conductor. So if there's a break in the skin, it may conduct more, but intact skin is considered as a bad conductor. It's not an insulator because there's a conduction, but it's not as good as the other metals and fluid. So insulation is the opposite of the conductor. So any material that does not give up electron easily is known as insulator. So glass, rubber, wood, so they are considered as the insulator. Now, the next thing is the resistance. So which we deal during recording. So we are stimulating the patient and we are recording. So our electrodes are attached to the patient and the signal is being transferred from both directions. So the flow of the signals, and there's always opposition to the flow, and that opposition can be opposition to direct current or alternating current. So if it is opposition to the direct current, it is known as resistance, and if it is direct opposition to alternating current, it is known as impedance. So if the impedance is very, very high, that means that our resistance is very high. That means that our contact of the electrode to the skin is very, very bad. So either because you see the patient, they come with the oily skin, or they have makeup, or they have very dry skin, or they have a dandruff, or sometimes they're in an accident, or they are immobile, so they have a lot of they haven't taken bath, so there's a lot of substance on the skin. So you have to clear the skin very well to make a good contact. And the symbol for resistance is R, and the impedance is again R, and the unit for measuring is ohm and kilo ohm. So the best thing, the recommended according to guidelines, that we should have a resistance or impedance below above 250 ohms and less than 2500 ohms. So any one of you is going to take an exam, CNIM exam or ABNM exam. So the number you should remember is the highest impedance allowed is 2500 ohm or 2.5 kilo ohms, and lowest is 250 ohms. Now we can say why we don't need zero. So we cannot have a zero impedance, because zero impedance means that there's a short circuit and there's no connection at all. So it's impossible to get anything with a zero impedance. Capacitor is another item in the circuit, and capacitance is a function of the capacitor to store the electric charge. So the time it takes the capacitor to store charge 63% is known as time constant, and that time constant is variable from one capacitor to another. So it's a bigger capacitor, it will take a longer time, smaller capacitor take a long time. But if you look at the picture, so the capacitor, the resistor are in sequence, they are connected, but capacitor, they are two plates, they are a little bit distance apart, they are not in sequence. So when you turn on current, the capacitor the first plate start charging, and it doesn't transmit the current to the other plate until it reaches the 63% of the total capacity. So once it reaches 63%, it starts discharging to the other side and the current will flow. So when you stop the current in the circuit, the capacitor will still discharge until it drops below 63%. As compared to resistor will not transmit. So there'll be zero current before and after resistance if it is turned off, but the capacitor will have zero before, but it will still have some current flowing after it is turned it off. So current, so we have current is the movement of the result due to movement of the electron. In a typical battery, the current is moving from positive to negative. But in the electric circuit, we describe in the neuromonitoring, we describe as the electron, they are moving from positive to negative, and the current is moving from negative to positive. So that's one of the reasons every time we do any stimulation, you do a pedicle stimulation or you do direct nerve stimulation, or so we always use or cortical mapping. So we always use constant current stimulation. We plug the probe or stimulator in the negative, not in the positive, because if you stimulate in positive, it's not going to work. So the electricity, and briefly, so I'm just not going to detail, but we can go into detail. So we have alternating current and we have direct current. So direct current is travel only in one direction, and this is type of electricity we see in batteries, or you have a laptop or iPhone, or they have a so those are they are running in a DC current, and they are very low voltage current. The alternating current moves back and forward, so positive and negative move back, and it changes the magnetic field around the wires and the circuit. So you have uh, so the you can so the alternating current moves in fluctuating mode, so it has up down, so the positive and negative keep fluctuating, while the direct current will have a square wave. So here we can see the alternating current is reverse direction in equal interval of time. So with the equal interval, the positive becomes negative and negative becomes positive. So it moves from negative to positive and then negative to positive in the other direction. On the other hand, the direct current, it flow only one direction, so it stays stable. It doesn't change the polarity while during the stimulation. Um, the next unit is the voltage. So voltage is itself is nothing, but it is a difference between 2 points, and that drives the electric current. So in the circuit, we have two poles, positive and negative, cathode and anode, and the difference between the two causes the voltage, and that voltage result in current flow between the circuit. So the voltage, if you want to increase the voltage, we increase the difference between the two, and that will result in the voltage. And the unit of voltage is volt V, and then we have millivolt. So one every volt has 1,000 millivolts, and every millivolts have 1,000 microvolt, and 1 volt has 1,000,000 microvolts. So we can stimulate the signal produced in the body is in microvolts, so they're very, very small. But when we are stimulating with motor evoked potential or something, we are stimulating with volts. So as we talk about the capacitor, so the time constant is the time it takes capacitor to charge is 63%, and it is inversely proportional to the cutoff frequencies. So when we are setting the frequency cutoff filter setup, we set up, it depends on the time constant, and it is inversely proportional to time constant. So time constant is equal to 1 over cutoff frequency. So if the time constant is short, the cutoff frequency will be higher, and if the time constant is longer, the cutoff frequency will be smaller. Now, if you combine all of these, we get to the Ohm's law. So I know this will be the most boring lecture because everything else is clinical. So this is electronics, but there are few basic description, and that they come in exam. So Ohm's law is described as V is equal to I into R, or V and E are same. So in the exam, sometimes you get E instead of V, which is energy, which is same as voltage. So voltage is equal to current time resistance. So we use the same formula for stimulating with the constant current stimulation. If you're doing a sensory evoked potential or sometime direct cortical stimulation, we use constant current stimulation. For motor evoked potential, we use constant voltage, but in some machine, we can also use constant current stimulation. So when we use constant current stimulation, uh, the current remains the constant, but the voltage changes depending on resistance. So we don't have any much control on the resistance. The only control we have on the resistance is that we can prepare the skin and make sure the resistance is very, very low, or impedance is very low. So if impedance is low, the voltage will decrease, and if your impedance is higher, the voltage will increase. So that will keep the current constant. So constant current doesn't mean that you cannot change the current, but whatever current you set, if you stimulate at 20 milliampere or 50 milliampere, that current flow will not change in the circuit, but it will change the voltage depending on the resistance of the electrode. On the other hand, if you are using constant voltage stimulator, we have the voltage is constant, so it is current time resistance. So the resistance and the current are inversely proportional. So if the resistance is increased, the current will decrease, and vice versa. So resistance decrease, the current will increase. And if we have voltage and current, both of them, we can find the resistance of the electrode. So any question about constant current stimulator, constant voltage stimulator? Okay. So now the next is differential amplifier, which get a little bit more complicated. So differential amplifier, they are built in op amps in the system. So technically, we cannot make any changes into the differential amplifier. We can change the current, we can change the voltage, we can improve the resistance, we can change the filter settings, but differential amplifier we cannot change. But it's important to know what is a differential amplifier, because your signal input and display depends on the differential amplifier. So the differential amplifier, it cancels any signal which is in common mode. And the reason is it has two inputs, input number 1 and input number 2. The input 1 is also known as active input or negative input or inverting input. So active, negative, and inverting is the same thing. And that means that any signal going into this input will invert its polarity. So if the signal is positive, it will become negative. And if it's negative, it becomes positive. So if it is a positive signal in the body, it will appear downward on the screen. And if it is a negative signal, it will appear upward in the screen if it is going into the negative input of the amplifier. If you put the same input, positive into positive input, it will stay positive, it will not change. And if it's a negative input, it will stay negative on the display. So depending you're plugging into negative or positive input, it will change the polarity. And if you have opposite signal, so it will become minus A plus B. So the input 1 becomes negative and then it's added to that. So for this one, if this is plus 1 microvolt and this is minus 1 microvolt, this will become minus 2 microvolt, because it's minus 1 plus minus 1 minus 2. But if they are both the same signal, same time, same amplitude, that means they are occurring in common mode. So this will becomes negative. So, and then when you add this negative to this positive, it will be cancel out. So that's one of the reasons when we're putting the electrode on the brain or then the muscle, so we are trying to get rid of the common mode signal. So if you want to be more sensitive, you move the electrode far apart. So there's a lot of difference in amplitude in the signal between the two. If you want to be very, very specific, you keep the electrode very close to each other. The other function of the amplifier is gain, and gain is how much amplification you are getting. So if you're putting the input signal is 1 microvolt and the output is 1 millivolt, that means the gain is 1000. So gain, the formula for gain is output voltage divided by the input voltage. So if input is 1 microvolt, input is 1 volt, and output is 1000 or 100 volt, so it will be gain is 100. So it amplified the signal. So you have two functions. One is common mode rejection. Common mode rejection is that any signal which is common mode, it will be rejected. And the second is common mode rejection ratio. The ratio means that how many times it gets rejected out of total time. So the minimum required according to guidelines and for exam purpose is 10,000 to 1. That means for every 10,000 signals, one signal will pass. So the error rate is 0.00001. So it is, so if it is rejected more than that, if you have 1 in 5,000 or 2 in 10,000, that's a bad differential amplifier, and we don't want that to be used. If it is better than that, so if you have 1 in 20,000, that's very good. So that's fine, but we don't want less than 10,000 to 1. So if you zoom in a differential amplifier, so differential amplifier is, the symbol is this one, so it just has a triangle with negative and positive input, but actually it has two amplifier inside. So it's a combination of two amplifiers, which is in this picture. So you have amplifier 1, you have amplifier A, and then you have amplifier B. So amplifier A has this negative input and this positive input, and the amplifier B has this positive input, negative input and positive input, negative and positive. So this is a very high, big resistor. It is connected between the positive of 1 and the negative of 2. And that the reason is it is known as input impedance. So if you're in an exam, most of the time, if you get a question about input impedance, this is the impedance at the input of the differential amplifier. It is not the impedance of the electrode. So, and it has to be 1 mega ohms or higher. So the requirement is to at least have 1 mega ohm or higher for differential amplifier. So if it is smaller than that, then the signal can come to the other amplifier instead of moving to the forward. So we want the signal to move more forward and not doesn't come back. So so the signal becomes negative here, and then it's added to this signal, and that's your output. Now these are few examples. So we have a positive signal, and it is inverted because going to negative input, and you have a negative signal which is getting inverted because getting that upside, and then the same positive signal, when it going to positive, it doesn't get inverted, it stay the same. And if the positive signal stay in the positive, it will not change. So that's one of the reasons when we are talking about the signals, you have N20 for example, for upper SSAP, it's a negative peak which is going up, but on the screen it shows upward. So any upward signal should be positive, but it is negative, label is negative, not because it's going negative on the screen, but actually it is recorded negatively on the in the body, in the brain. And any signal which is produced in the brain, it has dipole, which means that one side is positive, one side is negative. So the signal is produced here in the middle, it will create a negative side and a positive side, and depending where you put the electrode. So if you put the electrode on the negative side, we label it as N20. If you put the electrode on the positive side, we label it as P22 or P30, whatever. So if you have the same signal but in a different polarity, this will become positive here, and when you add 2, it become double. And if you have like a big signal in one side, +2, and this is +1, this will become -2, +1 will becomes -1. So those are just the samples, and you can practice more sample. Now this is so the gain of the amplifier, as we talked in the previous slide, is the amplification factor. So, and the formula for that is gain is equal to output voltage over input voltage. So the two formula you want to remember is Ohm's law, which is V is equal to IR, and gain is equal to output voltage over input voltage. So that's why we can make it clear. So frequency, the next topic we're going to cover is frequency. Frequency is number of cycles per second. So anything which is happening per second is known as frequency, and all the signals are in hertz, and the symbol of the frequency is hertz. Like actually, this is this hertz. So, and the time between the two peaks is known as the wavelength. So the wavelength is the time it takes one cycle to complete. So if this if one so if the signal is occurring 10 times per second, for example, 10 times per second, then the wavelength of the signal will be 1/10 second, which will be 0.1 second, and it is same as 100 millisecond, because there are 1000 millisecond, so 100 millisecond. If the signal is occurring after 20 microsecond minus 6. So now if you want to find the frequency of the signal which is occurring after 20 microsecond, so microsecond is 1 million. So you divide 1 million by 20. So you have 50,000 hertz. So if the signal is very, very small, it's 50 microsecond, 20 microsecond wide, then we need this. That means the signal is occurring after 1 million, 50,000 times per second. So the formula is easy. Just need to remember that when you're converting so you have frequency and you have the wavelength, lambda, and you divide both by 1 million. So if you want to change the wavelength to frequency, you divide 1 million by the wavelength. If you want to change the frequency to the wavelength, then you divide million by frequency. So you divide they can be alternately changed, but you have to divide 1 million by that number if it is in microsecond. If it is in a second, then you divide 1000 because it's 1000 millisecond, and then so if you get the frequency, so if the wavelength is 200 millisecond, and divide 200 by 5, so that will be 5 hertz. So that means the signal is occurring after every 5. So now we have this signal. So how the signal is sampled? So signal is occurring in the body, but we want to take the sample, computer change it to digital format, and then convert back to the analog, and then display. So the number of samples we take per second is known as sampling rate. And the sampling rate has to be minimum double the highest frequency in the signal. So if you have multiple signal, like if you're doing EEG, you have 2 delta, theta, alpha, beta. So you have 4 hertz, 10 hertz, 15 hertz signal. So you sample highest frequency. So you sample at double of the 15 hertz, because that will be so the question is, are you dividing it by 100,000? So if it is a microsecond, then divided by 1 million. So if it is microsecond, then you divide 1 million by microsecond. If it is a millisecond, then you divide by 1000. Depend what is the wavelength of the signal. Okay, so for example, this is a 3 hertz signal. So if you take 3 samples, same frequency, it will be a straight line, because the sample will occur in a same interval, fixed interval. There you cannot change. You cannot have a shorter, less time between 1 and 2, and more time between 2 and 3. So they will occur after 333 millisecond. So you'll have either it will occur on this spot, or they occur in top peak or bottom. So it'll be a straight line. So if you do a double the frequency, 6 hertz, so you may get 6 spots. So it will be a zigzag signal. So it will not be as good as the one, but that will be the most closer one. If you're doing like 4 hertz, the signal is for 3 hertz. Doing 4 hertz again, it will be sampled after 250 millisecond, and your signal will be distorted. So this distorted signal is known as aliasing. So aliasing is when you're not sampling at least twice the maximum frequency and you distort the signal. That's as aliasing. And if you do that, that's Nyquist frequency. But this is the minimum sampling. It is not the maximum sampling. So you can go faster than that, but you cannot go slower than that. Now, so yes, Safura, yes. Go ahead. You have a question? Sorry, I cannot hear you. You have raised the hand, Safura, but I cannot hear your question. Okay. Okay, we're going to talk about filters. So filter is when you're trying to get rid of something. So that's a filtering. And what happened is that because we have so many different signals and we want to focus on one type of signal, so we have to get rid of the other signal. Actually, Nyquist frequency is half the sampling rate. Actually, the question is Nyquist frequency is half the sampling rate. That's not correct because Nyquist frequency, so your sampling rate is the Nyquist frequency. So sampling rate is the Nyquist frequency. So Nyquist frequency is sampling twice the highest frequency in the signal. And so if you're sampling at twice the highest, then you're sampling at Nyquist frequency. If you're sampling at less than that, you're sampling less than double. So for example, if you're doing, we are monitoring the sensory evoked potential and we are monitoring from the scalp electrode on the head, but the head is also producing EEG signal. So, so head is also creating the EEG signal, and those EEG signal, we don't want to record those EEG signal while we are monitoring the SSEP. So we have to know what is the frequency of the signal. The EEG signal we record is 0 to 30 hertz, and the SSEP signal we record is about 100 to 200 hertz. So we want to get rid of, so we use a low cut filter, which is anything which is low cut is high pass, same thing, anything below that point will be cut off and anything below high. So use the low cut at 30 hertz and that will get rid of all the EEG recording from the brain. And then we use low pass or high cut. So we don't want EMG and the high frequency signal, which are also produced in the muscles on the scalp or the face. So we use about 500 hertz for high cut and 30 hertz for low cut. So give us a range which is known as band pass filter. So band pass filter is a bandwidth for which the signal is passing. It's a combination of the low cut and high cut. So the signal in the brain, they are gray matter signal, and the gray matter signal are slow. And the white matter signal are faster. White matters are myelinated fibers. They are dendrites and axons, so they oscillate at a faster frequency. So we use higher low cut filter for subcortical and peripheral responses, 1500 hertz. But for cortical, we use low filters, about 500 hertz. So the slope, so none of the filters are perfectly aligned. So if you set up a cutoff frequency, they're not going to cut off in 90-degree curve. So there's always a slope. And that slope means that the filter will stop cutting off before the cutoff frequency, and it will keep cutting off after that. So that slope is that's known as roll-off slope. So we can do a set point for high cut and low cut depending on like it's a second order or a higher filter. So there will be some kind of slope. But if you have a -3 decibel slope cutoff frequency, that means there's a 30% drop of the signal at that point with a -3 decibel. So the recommended filters for the low cut for IM is -12 decibel.
No puedo, porque por Zoom. Creo.
So -12 decibel for low cut and 24 decibel for high cut. So that's the recommended resolution. Now the resolution of the amplifier, resolution of screen depend on two types: horizontal resolution and vertical resolution. So we want to have, so we are going through signal, we are doing averaging, we are amplifying, we are averaging, we are filtering, and now we have to display. So display depends upon the horizontal resolution and vertical resolution. So the vertical resolution is running up and down, but the reason the lines are horizontal for vertical resolution are because every line is presenting one data point. So all these data points are representing your vertical resolution, and the lines which are running vertically, they are your horizontal representation because these are representing the data points for sample. So the horizontal resolution across the screen depends upon your analysis time or dwell time. Dwell time is the time between each sample. So dwell time is equal to 1 over sampling rate. So depending on how fast you're doing. So the minimum, actually the maximum sampling, the dwell time is 20 microsecond. And that is your CNIM exam question. And they say, okay, so you cannot have more distance more than 20 microsecond. That's the maximum allowed for any machine to record the evoke potential or spawn EEG. So anything less than 20 microsecond is fine. The distance between the horizontal point, vertical horizontal point, but more than 20 microsecond will distort the signal. On the other hand, the vertical resolution going from the points we have from top to bottom, it depends on the size of the analog to digital converter. So the analog to digital converter is converting the analog signal in digital format and is going to mark the data points on the screen. So how many data points we have, and the formula for that is 2 power 8, 2 power n, where 2 is the number of, so 2 times 8 means 2 times 2 times 2 times 2, 8 times, which is 256. So if you have 8-bit analog to digital converter, so you'll have 250 per point across the screen from top to bottom. If you use 10-bit, you have 1024 point. That means from the middle, you have 512 points above and 500 and the negative and bottom. If you use 12-bit, you have 4096 points. So more bits you have, better resolution you have because you have more points on the screen. So when you join those two screens to draw the image, so image will be more smooth instead of zigzag. Analysis time. So analysis time. So when we look at the screen, so we have screen for left hand and right hand, and left foot and right foot, EEG, EMG. So that screen is known as analysis time. For the other other use is the analysis time, sweep time, sweep, time base, epoch time. So there are different terms used, but all represent the same information. Hello? Okay. So, and dwell time, as mentioned before, dwell time is the time between two samples. So this is signal and you're sampling. So the time between two samples will be dwell time. And dwell time is equal to 1 over sampling rate. Or sampling rate is equal to 1 over dwell time. So yes, signal averaging. So now we have the display and everything. So everything is connected. Now we need to average those signal. And why we need to average the signal? Because the signal in the body is a very, very small signal. And the noise, we have background noise all over the room. So we want to get rid of the noise. So when we are hello.
शिफ्ट क्यों करोगे छोड़ दो उसको ऐसे
So if the signal is going to be the same, you stimulate 1 time or 100 times, but noise is random. So it could be +1, -1, +0.9, -0.9. So when you average that noise, it get filter out. So if this is the size of the signal amplitude and these are the number of averages, how many averages do, so that the signal will not change. The signal will stay the same, but the noise will be very high at the beginning. But with the average, it gets smaller and smaller, and it tends to zero. It never comes to zero, but it gets close to zero as possible. So more averages we need. It make so if we have, for example, so the formula we use is signal to noise ratio. New one which we want is equal to signal to noise ratio. Old one which was there, and you multiply with the number of averages. How many averages we have? So if the signal to noise ratio, signal is 1/10 of a noise. Noise is very, very high, and signal is one part, and you want the signal 2 times the noise. So you make it is 1/10 of a noise. You want double of noise. So how many averages you need? So that's another exam question. So we take 10 here. So it'll be 20 is equal to √n. And when you square both sides, so it'll be n is equal to 400. So you need 400 averages to make the signal twice if the signal is 1/10 of the initially. So if the signal to noise signal is one. Hello, Benshad? So if signal is 1/4 and you want the signal to 2 times, then you have 8 is equal to √n, and n is equal to 64. So you square those type, bring outside the square root. So you need 64 average for a signal which is 1/4 to make it a double of the noise. So that's the formula we used for that. So fast Fourier for transformation, so I'm not going to go into detail, but for the neuro monitoring part, so if you have not taken the exam, so the only question that comes in the exam is what is FFT, and FFT is the mathematical calculation and presentation of the signal due to analog to digital conversion. So that's the only thing. So this is a formula we talked. So the signal never changes because averages of 1 or 100 signal is always the same, but noise, the amplitude of the noise, it drops. So we want to have more averages for evoke response. So for spontaneous EMG, if you are doing EMG, spontaneous EMG, so that's fine. We don't want to change it. But for evoke response, so we change. So display sensitivity. So this is the sensitivity of the screen. So anytime you're open a computer and you're looking at it, so the gain of the differential amplifier we talk about, so gain amplifier, and that will affect the real signal. The signal is irreversibly changed. You cannot, the sensitivity is how it looks on the screen. So if the signal is 2 microvolt and your display is 4 microvolt per division, so there are 10 division. So every screen has 10 divisions vertically and 10 divisions horizontally. So in every single divisions you talk about, you have to set up. If you set to 4 microvolt per division and your signal is 2 microvolt, it'll take half of the screen. If you change the sensitivity to 2 microvolt, it will take the whole screen. And if you change the 1 microvolt, because the signal is 2 microvolt, it'll take two divisions instead of 1 division. So this is a zoom in and zoom out phenomena. So if the signal is very, very big, you change the sensitivity to a bigger number, so it make it smaller. And if the signal is very small, you change the division to a bigger number, so it take more, it will get bigger in size. So artifact reject. Before talk artifact reject, we go into dynamic range. So dynamic range in different computers is labeled differently, and it is labeled as input gain also, which is actually not a gain, it's a dynamic range. It is, so if this is your window, so dynamic range is the range in microvolt that will allow the signal to pass without distortion. So if the signal is 10 microvolt and dynamic range is 8 microvolt, so the signal will appear chopped. So it will be clipped. It's the term we use is clipping. So that the signal which 1 microvolt above and 1 microvolt below will be clipped. So the display of the signal will be clipping on the screen. So we want to have a dynamic range bigger than the signal, so there's no clipping. So every time you see you're doing a motor evoked potential or sensory evoked potential or any evoked potential, visually evoked potential, and you see clipping of your signal, that means the dynamic range is very, very small. But if you have a dynamic range very too big, then the sampling will also add the noise which is behind that, so it will cause distortion. So we don't want too much bigger signal dynamic range. Going back to the artifact reject. So artifact reject can be set to 90%, 95%, or it can be less than. So it is set in percentage. So when you set the artifact reject to 80%, for example, it will be the 80% of the dynamic range. So if the dynamic range is 200 microvolt total, then if you set the artifact rate to 50%, so that means any signal which is more than 100 microvolt will stop. So it's not going to cause clipping, but it's going to cause the averaging to stop. And it is done to get rid of the noise, because when you're doing bipolar or Bowie or any big noise, and you don't want to interfere with your signal and part of the signal, we use the artifact reject. And artifact reject will any signal. So you're doing 200-300 averages, and if the 10 signals are very huge and noise, they will pause and they will be not part of your signal. So the difference between dynamic range and artifact reject is the dynamic range is going to clip the signal, and artifact reject is based on your dynamic range, and it's not going to clip, but it's going to pause the averager. Talk about the resolution. So ground, we use ground. So the ground is used to get rid of the stray current on the skin. So when you're stimulating, the current is spreading on the skin also, the stray current. So the ground absorb that current, stray current, and decrease the stimulation artifact. If your stimulation artifact is huge, if this is your signal, and you see the stimulation artifact going across the screen, that means either your ground is bad, or you have a higher impedance on your recording electrode, or higher impedance on your stimulation electrode. So you have to check those things. So stimulation, so there are different types of stimulators we use. So we can stimulate with a monopolar or a bipolar or a tripolar electrode. So so if you when we are stimulating, so we have to stimulate with the cathode, and the return is coming from the anode. So if the stimulation is on the nerve and the return is far away, then it's a monopolar electrode. If both anode and cathode are on top of the nerve or stimulation area, then it will be a bipolar stimulation. And then bipolar stimulation can be bipolar straight ball tip. It could be a hook electrode. It could be a concentric electrode where the cathode is in the middle and the anode is surrounding that. So it has to be very, very precise electrode. Then we have a tripolar stimulation. And tripolar stimulation, both anodes are on the each side. The anode, we have two anodes, and in between we have a cathode. So that minimizes the current spread, and it is typically used only for brachial plexus or peripheral nerve repairs or nerve grafting. So we want to stimulate the nerve action potential. So we use the tripolar stimulation, and we use bipolar recording for these electrodes. Any questions so far? Yes. Hodgman works like bipolar. Can we use bipolar for direct cortical stimulation? Yes. So Hodgman, yes. Hodgman question is Hodgman works like bipolar. Can we use bipolar for direct cortical stimulation? So Hodgman probe, when we are going to cover the unit 12, I think, module 12. So Hodgman is used for direct cortical stimulation in a bipolar mode. And that technique is known as Penfield technique because Penfield technique is a 50 hertz stimulation. With the bipolar stimulation of the brain has a higher risk of seizures, intraoperative seizures. So that's why we prefer to use a Taniguchi method, which is a monopolar. So for direct cortical stimulation, we prefer to use a monopolar stimulation with a high frequency 250 or 300 hertz instead of bipolar stimulation, which is which is used as 60 hertz stimulation. We only use the bipolar for a language mapping. So if it's a language area, then we use the language area. So we'll do more detailed when we get to that point. So we have active and reference input of the amplifier, but we also have active and reference electrode. So the active electrode is different the active amplifier. The definition of the active electrode is the electrode which is close to the signal. The reference electrode is the electrode which is not close to the signal generated. And the pair of those two is known as montage. Montage is a pair of electrode which is being recorded. So we can plug the active electrode into the active input of the amplifier, or we can plug so if this is the active input of the amplifier, then this is the active electrode. So you can plug the active electrode into active input, or you can plug the active electrode into the reference input. And then you have a reference electrode. You can plug the reference into the reference input, the reference into the active input. So both actives and reference, one is for input and one is for the amplifier. So the recording types, so the stimulation type, we have monopolar, bipolar, and tripolar. And then the recording, we have monopolar, bipolar, tripolar. Monopolar recording or bipolar recording is that both electrodes are placed active and reference close to each other, either in the same muscle or same part of the brain to record EEG. Referential is that when you put the one electrode close in the one near the generator and the references away. So we have bipolar recording and referential recording, and we have monopolar, bipolar, and tripolar stimulation. So if you are doing monitoring,
I have a doubt.
Excuse me?
I have a doubt. Can I go? Can I ask?
Yes, sure. Go ahead.
Yeah, it's regarding the monopolar stimulator. You're talking about the monopolar stimulator. The stimulator has to be connected in the negative side of the, the generator, or because you're saying that the stimulator is cathode. I mean, it has a positive sign, right?
So when you are stimulating, so you have the stimulation output, you have positive and negative in your stimulation box. So
yeah, exactly. Yeah.
So probe should always be plugged into the negative. And
yeah, that is what we are doing.
The needle is plugged into the
positive.
So if you're doing a bipolar electrode stimulation, then both are plugged into. They are next to each other and plugged in.
Okay. Thank you so much.
So that's the stimulation, but the previous slide I was talking about the recording electrode. So this is the head, and you have recording from left cortex, and your reference has FPZ in the front. So this is the active electrode, which is close to the signal, and this is FPZ is a reference electrode. Now this
Yeah,
active
got
electrode
it.
you can plug into the active input of the amplifier. So this active
Got
input
it.
of the amplifier is different than the active electrode. So don't confuse the two actives. Many people they confuse.
Okay.
So, because many times I ask question, what is the active electrode? And people start writing about elective input of the amplifier, or vice versa. I say, what is the active and the reference input? I say, okay, active is close to the signal. So the active electrode is different than the active input of the amplifier.
Thank you. Thank you. Got that point. Thank you so much.
Okay, welcome. So the electrodes which we use are adhesive electrodes, surface adhesive, or the sticky electrode, and they're typically used for stimulation. They have a bigger surface area. So if you have bigger surface area, you can have less current density because you're sending the same current over bigger area. So less chance of skin burns. And they are adhesive, so they are more secure. The other one are the gold cup electrodes. So gold cup electrodes are cup shape and they have small opening. So you can fill up with a paste and place on the scalp or for recording and stimulation. They are reusable. So the other one is corkscrew electrode. So corkscrew electrode has a needle which is screw shape and is screwed on the scalp. So it's always used on scalp, not on the skin. And that is used for either motor evoke potential, definitely, because they have a bigger area of the current. So they have less current density. So you're stimulating at 500 volts. With the needles, you have more chance of skin burn than corkscrew. Corkscrew will have minimum chance of skin burn. So they are more secure. So we can also use for EEG and EEG and SSP recording from the scalp. And the other one are needle electrodes. So they are insulated. They are insulated except for the tip. So they are used for SSP recording, EMG recording from the muscle. Some people use that for grounding. It's not, I don't recommend using for grounding. Use the ground electrode because it has more surface area, get better grounding. And some people also use for motor evoke potential. You can use for MEP stimulation, but better to use with the corkscrew because it has a better, more surface area. Yeah. And this is the ground electrode. So ground electrode is a big electrode, and that should be placed between the first stimulation site and the first recording site. So this is a hand, this is the leg. If you're stimulating from the hand, and your first recording is brachial plexus, so you should always push ground here. If you're stimulating the foot and you're recording for pulmonary fossa, you should always put the ground and the shin, leg, so before the first, because otherwise the ground is not going to be very effective. This is another hook wire electrode. So this is a electrode which has small hook at the end, a small wire in the tree, and when you prick in the muscle and you take that needle out, it stays there. It will hook. So it's a very thin wire. It's a very precise and used for cranial nerve monitoring or pressing the electrode inside, around the eye or inside the mouth. This is the epidural electrode. So it can come in 1, 2, or 3 contacts. So this is like 2 contacts. So contact number 1 and contact number 2. So those are the 2 contacts. They're circular shape and they are placed in the spinal cord, epidural space above the spine, for recording the motor function testing, D wave from the spinal cord. So those are known as epidural electrode. Cotton mill electrode, if you have used them, so they are thin wire again. It is embedded in the cotton. So you can, cotton is very dry, so you soak them in normal saline and then place against the tympanic membrane, and you can record from the cochlea. We use for hearing test, electrocochleogram. We can also place inside the brain, and we can place on the optic nerve or auditory nerve and record the potential from there directly. Bar electrode has 2 contacts. It's like thick, hard bar, plastic. And then there are 2 colors, so you can use anode and cathode. So this is cathode, this is anode. So this is used for clinical testing. So you can just put a gel on the skin and stimulate from that. Cortical grid electrode, they come in different sizes. 1x4, this is 4 contact, this is 8 contact, this is 6 contact, this is 10 contact, this is 8 contact, this is 64 contacts, 8x8, and we can place on the brain. So they are used for placing on the brain and recording direct electrocardiography or doing phase reversal or motor mapping. So you can stimulate and record from them directly. And those can be placed for a longer period of time. You can place for 4 or 5 days in epilepsy unit. These cortical grids are placed directly in the brain. So the covered area is facing toward the surgeon, and open area, open exposed contacts are to the brain, and we can record from that. And so we're going to go more detail. So this is the ohms stimulator we talk about. So this is a bipolar stimulation. It has 2 ball tip electrode, and that is only used for direct brain stimulation. So ohms stimulator is a bipolar stimulation. The bipolar stimulation is just same thing, 2 bipolar, or it comes in a different shape, so it has more distance. And then you have a monopolar, which has the same probe used for Taniguchi or high frequency brain mapping or pedicle screw testing, which has only one. And then the next second one, the anode is used as a needle electrode. This is also monopolar. It's a flush electrode, which is a straight tip instead of ball tip. So it's used for stimulation of the peripheral nerves or cranial nerves in the brain. The same thing, ball tip to the brain. And so you have these monopolar electrode, straight ball tip, bipolar ball tip. Then you have 2 ball electrode. There are 2 electrodes next to each other. Then you have monopolar hook, bipolar hook, and tripolar hook. So hooks are used for peripheral nerve monitoring. And the hook can be in different sizes. So you can have a 90-degree hook, curve hook, and full hook. At the end of the course, we are going to talk about the small cord stimulator for the small cord mapping. And small cord stimulators are used for placing, they are placed on the spinal cord for the pain relief. So the patient who has severe pain in their back or hips or legs and doesn't go away with surgeries and medication, then you can place this electrode. It comes in like 4, 8 multiple contact, and this is placed on the spinal cord, and it's attached to a battery in the abdomen. And when the batteries turn on, it causes paresthesia and numbness, so it relieves the pain. So with the monitoring, so we can precisely localize where it's supposed to be instead of placing randomly. So we place it the accurate. So patient has pain in the right foot, you want the stimulator on the area of the right foot, not in the midline or left side. These are the long needle electrodes. So I published 2 papers on this one, and those are the only one until now. So they are hubbed, which are connected, and they are like split, so you can move them apart. And they come in 50 millimeter, 37 millimeter, and then 25 millimeter, 18 millimeter, and 13 millimeter sizes. So the patient has higher BMI, it's obese patient. And for some quadriceps muscle and thigh muscle, they are big muscles, and you might, or abdominal muscle, you might not be able to record with the regular small needles. So we use the longer needle hook electrode. So I have these 2 papers published again on the bladder electrode. So if you want to read that, they will be in your handout. So this is the stamped electrode, which is stamped on the Foley catheter, which is used for urinary drainage normally. So they come in different size 6, 8, 10, 12, 14, and 16. 6 is the monopolar, and 8 to 16, they are all bipolar. So you can place them and record the external urinary sphincter monitoring, because many patients, the spinal cord, they come and wake up with a urinary urogenic bladder, and we want to minimize any damage to urinary bladder. And so we don't want the patient to be wearing the diapers for the rest of their life. So we can minimize any damage by monitoring these electrodes. So we'll talk in Unit 8 about auditory Vogue potential. So we have these different auditory stimulation, and we have these gold coil fold electrode, which are placed on the cochlea and inside the ear canal, and they can be used for recording and stimulation. Then we have goggles. So these are goggles which are placed on the eyes for stimulating with LED lights for visual evoked potential. So they're flash red lights. And then we have ERG electrode. I don't know if you have used that. These are electroretinogram. So we're going to talk about cranial nerves. So these are ring electrode inside contact, Katai cable. So we place on the cornea and record the corneal response with the flash PEP. So it's just like a peripheral response, and it has to be very carefully placed because it can cause abrasions. So you place a gel and then a transparent tape. So we don't pay opaque tapes because it's going to block the signal with transparent tape. And then we have the last one, we have deep brain stimulation electrode. So we're going to talk about later. Just going through over this electrode today. So they come in different sizes, 4 contact, 8 contact, up to maybe 100 contact. So huge, and you can select the contacts on the left side or rotation contact. And they're micro electrode recording. So we do the micro electrode recording and find the target where they're supposed to be. So the FDA has approved the deep brain stimulation for many diseases, including Parkinson, dystonia, essential tremor, obesity, OCD, etc. And so we plant them and treat the patient, and they're connected with the battery. Okay, that's it. So that was just a review of the electronic part for today. So we still have one more week to go for the whole the first section to complete, and then we are going to. So I put this review in the middle, so you have any questions or want to have explanation, I can ask. Typically, we do the Zoom meeting at the end of each week before the exam. So weekend is the exam week, so you have all the assignment complete, and then the lecture review during the week, and the Thursday or Friday we'll do, mostly Friday we do the Zoom, and then Saturday, Sunday you have the time to review them and recording, and also take the test. So any questions today or any comments? No comment. Okay.